Welcome back. Let's continue with the invited talk of this session. So it's my pleasure to introduce İnanç Adagideli from Sabancı University. İnanç received his BS and MS from Middle East Technical University. Then he moved to Urbana-Champaign, received PhD from University of Illinois at Urbana-Champaign. Then he worked several places throughout Europe, Leiden University, Delft, Canada, British Columbia, then University Regensburg. Today we will hear about the Excitations from İnanç. A little bit change in the title, but dynamics braiding and time resolved detection of tidal edge vortices.
Thank you so much, Oğuz. So it's a pleasure to be here, and thank you for the organizers while he's here again for inviting me. So this is basically work done in various places. I would like to also acknowledge Erdal İnönü for, I was acting as a part of these ideas were developed while I was acting as Erdal İnönü chair. So now, because of that, what I would like to do is that I would like to start, maybe I also like to, before I start, I would like to acknowledge my collaborators, some of whom are here. So not these guys, Fabian Hassler, Anton Akhmerov, Aurelien Grabsch, Michal Pakolski, and Carlo Beenakker from Netherlands, and Hassler, from Germany, Paul Bayreuther, Yaraso Esmianko, Lim Wang, also from Delft, and Paul Bayreuther is now in Germany. Hassan Hussein Somek is sitting right over there somewhere. There he is. And then we have Ahmet Mert Bozkurt, who's sitting right over there. So those will be, I'll talk about their work a little bit. And Barış Pekerten is sitting in that corner. Now, the motivation is basically, again, coming back to Erdal İnönü. So usually I ask, but now I know that people got wise now, so you will probably know the answer. So this starts from the work of Erdal İnönü from 1953. So it was done in collaboration with Eugene Wigner. And basically this was on the contraction of groups and their representations. So this is well known for its contribution to mathematical physics. And here what he says is that classical mechanics is a limiting case of relativistic mechanics. Hence the group of the former, the Galilei group, must be in some sense a limiting case of the relativistic mechanics group. So basically saying that, we know the Galilei group, we know the Lorentz group, and so on and so forth. Since we know that at low temperature or low velocities, you actually get the Galilei group from, somehow we know that we have non-relativistic mechanics from relativistic mechanics, the corresponding groups must also actually somehow get into each other. And that he called that a contraction. So the main idea, what he did was that try to see mathematically what happens when you basically go to low energies and low velocities. So we know that and that was the answer. We know that you get basically non-relativistic mechanics. Maybe you might say that's boring, but actually if you do this same exercise in the presence of matter, and if you go to lower and lower temperatures and lower energies, we know that you get to a condensed state, and you get starting again renormalizations of your effective groups. You have the crystal groups and so on. And even actually, if you go to the even more effective representations, you see that actually Lorentz group and other things actually start popping up. And among other things that I would like to also mention, for instance, if you think about even statistics, right, you get the permutation group in 3 dimensions. If you go to low dimensions in 2D, you actually get to another group, which is called the braid group, that actually is much more richer, and you can actually get to have particles which cannot be characterized as fermions or bosons. So what I'm going to talk about, not in this level. So these are the effective stuff that you actually get when you go even lower energies and then lower velocities. You again get this Dirac equation start featuring. For instance, in this case of a 2D topological insulator or a quantum spin Hall edge, you basically have these edge states where the upspin electron moves that way and a downspin electron moves exactly the other way. It looks exactly like a one-dimensional Dirac equation. Same thing if you think about a 3-dimensional topological insulator. You again have an effective surface state. In this case, it's not an edge, it's a surface. And it's a 2-dimensional Hamiltonian. Now, if the spin is that way, the particle moves that way. If the spin is that way, the particle moves that way. And it does that all the time. And if you look at the effective description, it looks like now a 2-dimensional Dirac Hamiltonian. Now, you can actually continue this thing, and then you can go to even higher dimensions, our normal 3 dimensions. You can actually get to effective crystals that feature Dirac Hamiltonian, indeed, exactly at their band touching point Like graphene is one, but this is in 3D, so there's 3D Dirac Hamiltonian. And you can actually go to some other things, in which you actually can separate this Dirac Hamiltonian into left-handed and right-handed parts, and then get Weyl fermions. And then you get basically Weyl semimetals and so on. So now today what I would like to, and you get actually most wonderful phenomena from these. And one of them is basically this, which I'll be talking about. This is from a cover of Science. It's not from the cover of Science. It's actually the original fake colored picture that made it the cover of Science when they faked it. So this is basically a nano device in which you have a nanowire here with some superconductor at the edge, and you apply magnetic field, and you get to this, hopefully to this phase of matter where you have a topological superconductor in 1D, and in this case the edge states turns out to be Majorana particles. Today I will be talking about that, but Barış here will also talk about a system like that. So he did this about finding disorder effects on this wire, and today he will be talking about the same thing but in arbitrarily shaped wires and how the parity crosses. What's that?
I have a postulant, not a talk.
Okay, sorry. He will be talking to you, let's say, if you ask him questions, if you wish. Okay, great. Thank you. Now, the next thing is that, and Ahmet Mert Bozkurt will be talking, you can do actually some implementations of Maxwell-Demon in the quantum spin knowledge. It's the two-dimensional topological insulator. And in which case you can actually, instead of storing energy, you can start storing information, and on demand use that information to convert heat into electrical current, which means that you basically store energy without storing energy. So you basically store in some sort of memory of a Maxwell's demon. And that all will, Mert will have a poster on that, and then hopefully he will talk to you if he's not too tired tonight. And then finally, of course, for this thing, nobody's talking about that today, but you can actually do stuff like spin transistors, other nice applications from this 3D topological insulator surfaces. And then also this, while Dirac semimetals, you can actually do something called the Weyl superconductor. It's a new phase of matter. And then you can actually, it has very nice features, like it can actually feature a vortex lattice, and in that vortex lattice, for the first time ever, it also features Landau levels. That's the only time a superconductor features Landau levels, which is actually has very nice consequences, which I will not talk about. But I would just, since this is basically also quantum applications of quantum, what it does is that actually, as you many might know, superconductors don't show any thermoelectricity, but this one does. And because of a reason that is not complete, that is completely absent in all the other thermoelectric materials. Okay, but what I would like to talk about, what I'm going to talk about today is the Majorana stuff. So there is the wire, there is the guy. So this was basically a very old paper. He did it and he got lost, and paper was also lost. And this was very obviously lost because nobody even bothered to, it was just in Italian as far as I know, and nobody even bothered to translate it. So it was really, really, really lost unless you're Italian and knew about it. And apparently if it was not known, somebody would be translating it to English. So what I want to talk about is, of course, start from this is something that I would like to remind you is this thing called the fermion, right? Here is a fermion. I know I can actually generate some sort of bound state. And then if there's only one, I can actually think about this as a single fermion state. Then I would actually define an operator that will create a particle in that state. Right? So without anything, this thing would basically create an electron there, or one fermion there, and the Hermitian conjugate would actually destroy an electron in that state. You can actually have many of these, and the fermionic statistics follows, as we all know, from this anti-commutation relation. So now, what is Majorana here? The Majorana is actually, whenever you take that operator, right, any Hermitian or any non-Hermitian operator, you can write it in terms of a Hermitian and anti-Hermitian part. It's just a mathematical trick at this level. Nothing really special. And if you just follow to be able to conserve the commutation or anti-commutation relation of these fermions, these operators, we now call them Majorana operators, have to satisfy this algebra. So they must anti-commute, but they would square to 1, right? Or 2 in this case, at 1, depends on what sort of normalization you're using. And now if you have a Hamiltonian, right, of a single electron, the simplest Hamiltonian you can think about is that you have an energy state where the electron is occupied, and when it's unoccupied, it has another energy state, only 2-state system. Right? This is basically something very useful for maybe quantum computation. And this you can write it in terms of a coupling between the Majorana, product of two Majoranas at the same point. Right? So this is the general thing. Now, if you want to, the whole point at this point is that, the Majoranas are just there in every electron you look at. But what makes them really special and what is we have this, you know, what is the storm in a teacup, or you know, what is actually generating this problem, you know, why people are so excited about it, is when you can actually start to separate them, right? When you separate them, so this is the two Majoranas, this is my single fermion, is there a way that I can actually move one here and the other one there, right? So then you can think about something which is localized in this point and at that point, but only together they make a single electron, right? On their own, they're not even anything. So that's why sometimes people call that Majorana zero mode or something like that, and I'm trying to avoid the word state or real fermionic state, because it's not a real state. Only together with the other one will become a proper quantum state. Now, how you can do that? Here it is. So there are two of them. So I know that, you know, all alone, I cannot really do anything. I know that electrons cannot be divided. So here is something that what I can do is that I can imagine a coupling between this Majorana here and that Majorana there. And since I did it once for these two, I know the form of that coupling. It has to be in this form, gamma 2 times gamma 3. And then when I do that, and then what it does is that it actually tries to get this Majorana and that Majorana, forces them to make an electron out of them. And then you take the T to infinity, it will actually get you a really nice new electronic or fermionic bound state, and this energy would be very high or very low, would take you off the low energy effective states. Now you have one unpaired Majorana here and another unpaired Majorana there, where you might say, well, these must be really nearby. So how can I actually do a little bit better? And the way to do that is that once you get the trick, you can actually imagine many of them in a row and then start binding them together in this form, right? Here it is, that's the binding. And then if you bind them and take the coupling to infinity, you would get, again, effective unbound Majoranas, this time very well separated. Now, there is no limit to your separation. Now, the question, the million-dollar question is, what is that Hamiltonian? That Hamiltonian is this one. It basically looks like a certain type of P-wave superconducting mean field Hamiltonian. Right, so, and also known as sometimes Kitayev's toy chain. Right, so this way you basically just get it out of your requirements. It will just, you know, basically that's the Hamiltonian unit. So other things that you can actually do this by putting if you have a topological superconductor and if you put a vortex sometimes, that also binds these type of modes, which I'm going to talk about in a second. Now the question is, what do you do with them? I don't know if you can really read this picture or you can see what it is. So it is basically something like, I think the Turkish one is not quite exactly the same thing, right? The Turkish one is something like bul karayı, al parayı, right? So that's the trick, right? It's basically cups and balls. You basically have this ball, there are various types of the game. You put a ball there under the cups and then you move the cups around, right? And here is then this was a magician, I think this is from the 19th century, and then you would guess where the cup went, right? So that's and the magic is that, you know, you have to move the cup to a point where nobody expects, right? It actually here, obviously, and since exactly like all magic and wizardry, there are actually some solid science underneath it, and the science here is the following. So now, if you take these Majoranas, right, they're actually, I can have them. In this case, I'm thinking about any way that I have to bound these states. And basically, remember, two of them makes a real fermionic state. That's the two-level state that are here, and the other one here. So what I'm going to do is that I'm going to label them even and odd. And if it is in the lower energy state, I'm going to call that basically plus. And when it's up there, I'm going to call it minus compared to fermionic. Actually, it's related to fermion parity. But you know, at this point, it doesn't really matter. So now what happens is that you do the exact same trick that these cups and balls guy do, right? You take one of them and then you just move it around the other one and then bring it back. So this is all four of them are here. You take one, move it one around the other one and then bring it exactly to the same point. They never come together. The state, on the other hand, you see that this will start out as basically the even state, or like let's say you have a fermion here, no fermion there. You see that that state ends up there. The effect of that thing, they never got to get close to each other. It moved one fermion from this set to that set. So now there's, of course, underlying reason, and the reason is that these things are actually very complicated objects. You have to define these branch cuts and things like that, which I'll come back to that. I'll actually show you how this actually, in Hamiltonian language, how it works. But you see that this is exactly what you want if you want to do quantum computation. The biggest problem is that we want quantum computers or whatever, that all information is very fragile, should not couple really strongly because it will decay and so on, it will go away. But at the same time, if you cannot couple to it, you cannot operate on it, right? So that's the problem. So here, you couple to them, so they never come closer, so you can operate on them strongly, but at the same time, they never come close, so they can never be operated by the environment. Only with these movements and only with this type of braiding operations, they're called braiding operations, they can actually, you can operate on the quantum state of these things. And you can actually put as many as you like on this. So you can actually imagine doing quantum computation by just moving them around, and that is the main idea behind basically Microsoft's let's say, decision to pursue in the realm of quantum computation, and this is basically this topological quantum. I think the idea not developed, but people like field medalist Friedman and so on, they were already been thinking about this thing, and now it's becoming closer and closer in terms of experimental things, but not too close. Now, let me just tell you how this works. I just want to say, just a few things about how this works in terms of, real Hamiltonians and so on. Think about the following. Now, I have these Majoranas also in a set here, right? In the previous one, I had to move them around with this, maybe some vortex, and I have to somehow control this vortex. If it is like this, you can actually control them by moving the gates and so on. So but it's actually, this moving them is a tricky thing. I'll come back to that at the end of this. But suppose I manage to do this. Right, every 2, I have to write a 2-state system, right? Gamma 1 and gamma 2, even fermion, odd fermion. Gamma 3 and gamma 3, even fermion, odd fermion. Gamma 5 and gamma 6, even fermion, odd fermion. They all have their states. Now, what I do is that I want to do this braiding. I just first take this gamma to this end. It's sometimes called after the guys. It's not the guy that invented, but he was there all in the beginning, and he was like contributed big time to ideas. Jason Alicea. It's sometimes jokingly called Jason's parking lot, because the effect is basically you're parking your car. Here's the movement of one braiding here, and then you take the second Majorana that way and then move this back. And that gives you some sort of a braiding operation. They exactly exchange their position. Now let's just imagine what would be the most, imagine this only includes 2 Majoranas, and I can actually take the other ones to infinity. So then you can imagine this has to be given by a unitary operation, right? And that unitary operation has to include the only relevant 2 Majorana operators that you have locally, right? Nothing else can be there because everything else is at infinity. Now this is the most general unitary transformation you can write, and you can see that how this unitary transformation actually transforms your Majorana operators themselves. This is just a very simple arithmetic. It's actually based just Pauli sigma matrices arithmetic, right? Algebra. Now this takes you gamma n to cosine 2 beta gamma n minus sine 2 beta gamma m. So it kind of makes a rotation between them. Now, if you want to actually exchange them, gamma n has to go in some way to gamma m, and gamma m has to go to gamma n, and that corresponds to this beta being equal to pi over 4. So in that operator performs the exchange. And there is a very important, and this is a necessity, all-important sign here, and that sign change does the trick of converting this one fermion from one place to the other. Right, if you do this, you can actually do, and this is, and these operators actually follow all the algebra. It's a representation of the braid groups. Actually satisfies all the algebraic properties that you want to expect from imagining this is a braid group. Like, if you can write it in terms of braiding in a certain way, and that's equivalent to braiding in another way, the corresponding operators will satisfy the exact same algebra. Now, what it does here is this U12, right? If I apply it, so this is my 4 Majoranas here, and these are the states corresponding to gamma 1 and gamma 2, and this is the state corresponding to gamma 2, gamma 3, and gamma 4, right? These are the even and odd states. Now, if you braid them together, you see that this is the operator. I know that I can apply the operator, get the answer. What it does is it gives you a phase, right? It gives you a phase based on the occupation number of the state formed by gamma 1 and gamma 2. The same thing if you braid 3 and 4, it gives you a phase based on the occupation number of the second one. So far they look like basically like anyons, right? You just get a phase, not necessarily -1 or +1. But if you try to braid gamma 3 to gamma 2 and gamma 3, and you actually exchange them together, you see that this thing, gamma n1 and 2, would take you to something which is the superposition of n1 and 2 and 1 minus n1 and 1 minus n2. This is necessary, right? It will take, if you're in 1, 1, it will take you a superposition of 1, 1 and 0, 0. If you're 1, 0, it will take you to a superposition of 1, 0 and 0, 1, right? And the reason for that is that total fermionic parity has to be conserved. all fermions have to come from somewhere. So you start from an even fermionic parity, has to be, final state has to be an even fermionic parity, except that you can redistribute it in a basic topologically protected way. That's the idea. Now, so that makes it a non-Abelian anyons because if you think about these operators, they don't commute, so the order that you actually do the operations actually matters. So you braid, so therefore these particles would remain basically aware how you actually exchange them in the past. So now how to understand this is indeed with this kind of this branch cut structure. Whenever you exchange them, whenever one of these gammas cross the branch cut of the other one, it picks up a minus sign. That's basically a computational trick that you can actually make it work to remember, what is the, underlying, basically algebra that does this. Now, so this is the big problem. So the Majorana bound states they're bound, right? You want to move them, that's the only way you can braid them, but they're bound states, right? They're bound modes, or whatever you want to call them, they're something bound, and you made it bound, and now you've worked so hard to make it bound, and then you want to actually move it around to other things, and that became a very problematic thing, right? So that's and that is the basic topic of my discussion today, is that no one managed to move them around so far, even if it is there. And there is actually all the proposal about moving them around actually is not about really moving them around, doing some equivalent stuff that looks like as if they moved it around. So by controlling the interactions and everything, all sort of other things. So now, if you cannot do that, can we just find a Majorana that moves? Right? So if it is, so far we only had a bound state, right? They're like stuck there. But if you have something that moves by nature, then maybe we would be able to do this braiding very simply. Right? So that's the question I would like to ask, and that brings us to this. So here is a moving mode, right? Instead of I was talking about a state, now I have to move a one-dimensional topologically protected mode. This is a Dirac equation, so basically it's a one-dimensional Hamiltonian that moves only to the right. It's a chiral Dirac Hamiltonian. Now if you go to do this in a topological insulator, you can think about, again, this Dirac mode as a sum of two Majorana modes. Right? So this is the same thing, like you can write every fermion with two Majoranas, just like that you can actually write this as two Majorana modes. Right? This is not the Majorana 0 mode, this is a Majorana mode. Now, if you then think about this and somehow isolate one, and that would be the edge state of a super topologically, basically topologically non-trivial superconductor. If you do that, actually, you would be able to get something that moves and has the name Majorana on it. Right, so we'll see if that actually braids. Now here it is. So the idea is that if you can do this, you can imagine injecting this Dirac mode here. It will come in, right? So this is an electron coming in, but this is now electron, right-moving electron mode. And if you actually have an interface between this topological insulator and a topological superconductor, this one would just turn because it cannot enter a superconductor, and the other one would go in. So this is an amazing thing. You basically have an electron, you separate it all the time into two. And this is an amazing, and this showed up for a while back. It's in these proposals, Akmerov, Nielsen, Beinecker, and Fu and Kane. And the papers, relevant papers, actually appeared within the day on the archive. Right? So that's a kind of a, and they actually very nice scientific collaboration. They actually also point they're both PRLs, they just point to each other about, they also see this article and so on. Very nice, very kind. Now, again, remember this gamma is gamma dagger. Now came out another thing from Susheng Zhang, and he said, basically, then I can braid them, right? That's the main thing. We propose a platform of quantum computation using the chiral Majorana fermions and isotopal material ball. Right? So this is basically proceedings of the natural economy of sciences. So therefore, you see the reviewers from EF, University of Illinois, and from University of Tokyo, Riken, and then FC from Kavli Institute for Theoretical Physics, China. So you can actually guess also the referees, which I think is not maybe such a bad idea in most of our papers. It would be nice to know the referees. Now here it is. There comes the idea. So what they do is that they just generate this topological insulator state and a topological superconductor and a topological insulator. And these both, they again separate at the border. That is the main idea. Now, if you actually write it like this, so if you think about the electron coming in, right, you have the gamma 1 and gamma 2, and if you trace the path of the gamma 2, actually gamma 2 goes to the other end, and the gamma 3 comes from the other end there, and it looks exactly like as if you're braiding these two, right? And then they come and say, yes, this is braiding. So now there's only one little thing, and then of course there's even an experiment for this thing, by the way, and that has I heard has some issues, so I'm not going to go too much into discussion. Anybody wants to learn more about that, I will be happy to discuss it after the talk. So the main problem here is that Majorana fermions don't have non-Abelian statistics, right? Majorana zero modes do, but Majorana fermions don't have it. That's why they're called Majorana fermions, right? They are fermionic, they have fermionic statistics. Right, so, and that is actually written like this. This is the Majorana mode. You write in momentum space like that. Remember, gamma dagger of K is not equal to gamma K, right? That's the quasi-particle, right? Gamma dagger creating a Majorana quasi-particle in this case and positive thing would be equivalent of destroying a negative energy one. Right? That's actually what it means to have a real field. But it means that gamma dagger is not equal to gamma K, so therefore the quasi-particles, they don't feature non-Abelian statistics. So that was a big thing. So what are we going to do? And this is basically, this is my main thing. So I'm going to propose the following. I'm going to say the edge vortices, some other excitations on this edge actually does the trick. And these are, to understand that, think of the following, basically, basically let's say Gedanken experiment. Suppose I have a topological superconductor and a Majorana state lying outside. Right. Outside, I have a trivial superconductor and a vortex in there. Right? Trivial superconductor have vortices, and somehow I managed to push that vortex in there. So now the thing is that a vortex in a topological superconductor binds a Majorana zero mode. Remember, a Majorana zero mode is not a real electron, cannot stay on its own. It doesn't make any sense. Right? So there must be another one, and now the question is to the audience, where is the other one? Anybody? So I'm just telling you that what I managed to do is I started with fermions and somehow lost half of them. Lost half of one of them, at least I lost half of it. Any idea where it can be? So actually, where it is, oh, you were saying so? Oh, you said 5 minutes, sorry. Yes, it's the edge, right? So that's whenever you do this, there is another one, completely delocalized Majorana mode at the edge. Right? So if you actually try to do this, remember, this is a very simple thing. It's like this. It's a one-dimensional mode with periodic boundary conditions, or anti-periodic boundary conditions, or which one? So now the trick here is that the difference is actually told by how many vortices you have in there. If you have odd number of vortices, you have periodic boundary conditions, so therefore you actually have a zero mode with any quantization of this. Whenever you have no or even number of vortices inside, you have anti-periodic boundary conditions, so there are no zero mode. So there are no delocalized Majorana mode here. Now this is the idea, but then imagine what happens here. Imagine I'm just like doing this. This is an enormously big thing, and I just injected this vortex there. Remember, this is actually a 1D thing. It's like basically, it is basically a relativistic system that moves with the speed of light equals to the Fermi velocity. So nothing can travel more faster than the Fermi velocity in the system. So therefore, whatever you do here, whatever imprint you do has to be localized here and actually has to go with the speed of light, or Fermi velocity. And that is the edge vortex, that imprint. Now, what is the amazing thing is that that imprint is a non-Abelian particle. So now, before I do this, I would like to tell you, of course, this 5 minutes is great. So I would like to talk about basically our proposal, right? The one thing is that, of course, you might say that, well, this is not an easy thing to actually push a vortex in, right? How are you going to deterministically do this, right? You may want to put it in a magnetic field, but then these things just come and go. You know, there's also, even when you try to do quantum phase slips, they're really like fickle and they're not really controllable. But there's actually one way to inject this deterministically, and that's with a Josephson junction. So what happens here is that you basically have these two edges, right? I have this, remember I have two edges in the original thing, right? Here, these two edges. But what I want to do is that I would like to have them separated by this topological superconductor. So I have one Majorana mode here, another Majorana mode there. Right, this is now a superconductor, and now I actually put a weak link here and then form a Josephson junction and apply a voltage pulse to it. Or I can apply, of course, a flux bias pulse as well, equivalently from a squid. But the voltage pulse, and then I make it such that the integral of this pulse is quantized. Right, this I can do that. What it does is, of course, remember, whenever you have a Josephson junction, if you apply a voltage bias, it just tries to turn the phase of the one relative to the other. if it is quantized exact, it will turn it exactly by 2 pi. And that's the trick. And the nice thing here is that, remember, superconductor phases, they want to be locked together. So therefore, even if you're not quantizing exactly, it will still go and lock more or less exactly at 2 pi. And that is a very important thing. Now you can deterministically do this, and you can convince yourself, actually, the effect of this, by changing the phase of this pi by 2 pi, changes the vorticity of this side relative to this side by 1. It's exactly the same as injecting one vortex across the junction. It's called the Josephson vortex. Now, you have this, you do this, and then the imprint here then would be your edge vortex that will just move through. And then it can, for instance, in this case, if you have a bulk vortex, can cross through its branch cut and do all sort of nice things. And then you basically you should be able to then braid it and then check how non-Abelian it is. Right, so that's precisely what we did. I'm just going to show you the main idea here. Right, here is basically this is a topological insulator. Here's the Dirac edge mode that goes that way, and this edge mode you split here into these two separate things. And here you have a Josephson junction, and then these two superconductors are grounded, and you need 3, and there's a very good reason for that. If you don't have 3, you put a voltage here. If you're a real conducting thing here, it will just go through, right? You will no normal thing that if you're applying a voltage to a conductor, you would get some current. But if you have a superconductor which you grounded, all the excess current have to be grounded, so there can be no current that naturally goes to the other lead through here. Only whatever is carried by the edge stuff. Now you apply this pulse vortex here, and now you have this injected vortex here. It goes around this vortex there, and then what you do is that it braids around this vortex. It will join forces together and then convert to a charge excitation, which you can detect. That's the idea. Now here's the prediction. So this is a simulation that you can actually calculate the S matrix from this thing. So this you can do it first in frozen S matrix thing, and later on we have a full, like if you don't have this adiabatic limit, you just have an arbitrary time dependence. You also can get an S matrix in many-body language, which you can exactly derive for this question, which is actually quite an amazing thing. I was not hoping for that, but you can, it's a very nice outcome. Now what you do here is that this is the scattering phase shift. If you have no vortex, you see that the scattering phase is exactly 0, and then you have, if you have an odd number of vortices, you see that the scattering phase shift winds from 0 to exactly 2 pi as you wind the Josephson phase. Right, what this means is that you basically, and here you use this thing called, basically adiabatic pumping formulas. You basically have, these are basically formulas that you convert scattering matrix into pumped current. If you do this, you basically can immediately calculate your pumped charge. That will be exactly equal to this, related to this angular difference between those 2 points, and this will give you exactly E. If you have odd number of vortices where you braid, gets you 0. So you basically have a charge readout already in the system. So now with that, how can you, of course that's the trick, right? You can ask the question, but I'm braiding them to a bulk vortex. Can I braid them around each other? It turns out that you can. You do the same thing by introducing some delays here. So for instance, I don't think I have a lot of time, so I won't tell you the math behind it. But I just want to say that you can actually exactly calculate the effect of this junking, like shaking the entire Fermi sea here. But if someone is interested, I would like to talk about it. And the main thing is that you have this initial ground state that maps into some scattering matrix times the ground state. That's scattering matrix. That's the many-body scattering matrix. And the nice thing is that you have an exact formula for that. So this is the field. Alpha is exactly something that you get out of your Josephson junction. And this rho is the normal ordered density. And this formula here is the exact scattering matrix. So you can actually calculate everything that I have been saying by just using normal turn the crank stuff. Now, the only thing that I would like to say that, and this is about the relation to Susheng Zhang's proposal. Now imagine if this alpha, right, this phase of this thing, instead of winding by 2 pi, if it winds by 4 pi, right? 2 pi and another 2 pi, you can actually show that this operator is related to the fermionic or the fermionic operator. It generates a delocalized fermion in the 2 Majorana modes. This is why Susheng's thing didn't work. Because basically, whenever you try to put an electron, it corresponds to a phase wind of 4 pi, so it has 2 branch cuts. So whenever you cross 2 branch cuts in a row, it never gives you any of this Abelian stuff. Always gives you normal fermionic statistics. And that's basically, you can actually see it already from this thing. Now, this is known as actually, it turns out it's actually a very strange derivation of the well-known bosonization identity in this context. So you can see there's a very nice review by von Duff and Scholler. Now, you can actually look at this, and then this formula here would tell you how the phase field of the vortex actually winds in, for instance, a system like this. Without the bulk vortex, you have a winding to pi and then back to 0. With a vortex, it will wind by basically pi and another 2 pi. So that's and that sign change is the effect of the braiding. And the same thing actually happens whenever you do this fusion. You can actually have this exact analytical charge current formulas, which I'm not going to tell you. The only thing that I would like to tell you here is that if you use these formulas, you see this every phase wind corresponds to half a charge. So this is basically the moving version of fractional charge of Jakob-Rebbe fractionalized charge, but now they're moving to the right. And whenever you separate them, you get the edge vortices. It's just like you separate Majoranas. Now, you do this, and the trick here is that whenever you have a kind of an edge mode, you can actually braid them. I just want to show you how you do it, and then I'm going to stop. So whatever you do is that you have a Josephson junction here. You inject these two vortices, and they're the branch cuts. They will move through. And because of this delay, the one stays behind, the other one goes through, and then at that point, you inject two other vortices. And then you get them delay back so that this stays back, and then you again bring these red ones together, and then when you join them, they would give you a signal, right? So therefore, you braid them. Now, you actually can calculate this. So this is the word lines of the same thing to show you that it can braid. And indeed, depending on this time delay, on how much of this, at what time you inject the second vortices, you see this first sign, which is just maybe a negative electric charge of E/2. Whenever you braid it in the right moment, when you inject these things, you immediately give you a positive charge, indicating full braiding. So now with this, you can do the same thing with a single edge. And now what I would like to do is that I would like to conclude. So basically, I mean, the whole thing is there, right? So I talked about bound Majorana particles, and I, talk about Majorana fermions, which are not non-Abelian particles, and I show you and hopefully convince you that actually the other excitations at the edge actually are non-Abelian, and you can be used for topological quantum computation. And the nice thing here is that it's just this one system which is actually implementable. So I'm hoping that this would be the thing that opens up the whatever is blocking the topological quantum computation. Thank you very much.
Do we have some experimental examples of a model which you proposed to realize?
Yes, there is. So that was actually even made the news and the science as the angel particle. There was the God particle, now Su Shengzhen called the angel particle. But there are problems. So they have basically a quantum anomalous Hall state in which they put a superconductor in the middle. And then the idea is that if you see this splitting, then you should see a charge quantization. The quantum Hall would quantize with units of conductance quantum. You would see some here quantized with half the conductance quantum. And they did see this. Now the problem is that there is an alternative explanation if you have these two quantum Hall states which are charge quantized by units, and if you put two conductors in a row and something that is dephasing in between, that also reduces the conductance by half. So that's the kind of the other explanation, and that was not so clear. And there also I heard other problems with that experiment. But the main thing is that I was just in Trieste talking to Lawrence Molenkamp, I think 2 weeks ago, and he was showing this data that he actually can dope a quantum spinol state with manganese magnetic atoms, and then you can actually then get a very low magnetic field quantum Hall effect. If you have such a low magnetic field, then you can easily, and he has the ways to actually inject some superconductor to actually make these edge states exactly work. So actually, and I told him he can be the next braider, and he liked it. So I can see that. So I hope
to the topic which you said that topping by some magnetic.
It's unpublished, but it's unpublished work. But I can if it is published, I can send you the reference.